entirely formal. We might cut it short, though. Let's see. Somehow what we're aiming for is we had two sets of examples of Lie algebras. Some of them looked like GLN, SLN, SP, 2N, SO, well, SON. And some other looked like TN, DN, and N. And remember, these were triangular matrices, diagonal matrices, and upper triangular matrices. Somehow what we're aiming is to say, well, let's divide all the examples of Lie algebras into two classes, some like this and some like this. That'll take a few classes, but let's start with a couple of examples. So, lemma. Let A be an operator, so an endomorphism of V, such that A is nilpotent. That means just that A to the n is equal to 0 for some n. For some n large enough. Let's suppose this V is finite dimension. Then add A. Remember, this is again an element of GL. Is also nilpotent. This is a confusing statement. So I have a matrix that acts on a vector space, say by multiplication. So you can think of this A. It's just a whole matrix with some entries, and it acts on the vector space V, which are just row vectors. And if you just multiply this matrix n times, this guy is going to be 0 for every vector. And the statement is that, well, actually, if you just now take this matrix and commute it with another matrix now. Remember, this was taking the adjoint. Is take the bracket. And take the bracket again with the same matrix A. And take the bracket again several times, n times, well, probably more than n times. This is also going to be 0. So that's a statement of this lemma. Let's prove it. Actually, this is a very simple statement. What does it mean to take the adjoint? The adjoint is in a very precise place. It's in GL. So if you remember, the bracket is multiplications and then multiply them in a different order. So the adjoint of A acting on B is, by definition, this is A times B minus B times A. Or which is the same thing as multiply on the left. So left multiplication by A acting on B minus right multiplication by A acting on B. So these are just the operators. These are endomorphisms of, well, GLV, which are LA of B is just AB, and this is RA of B is just BA. So far I'm saying trivialities. But the point is that these operations, LA and RA, are nilpotent operations. Well, indeed. Because LA to the n is just the operation of multiplying on the left n times by a. So this is just the same thing as left multiplication by a to the n, which is the same thing as left multiplication by 0, which is just 0. The same thing for right multiplication to the n. This is just right multiplication by a to the n, and this is 0. So I have two nilpotent operators, and I want to claim that their sum or their difference is nilpotent. Well, if I am to take a power of this and say, well, I want this some power to be 0, well, that would be quite helpful if these two guys commute. If there were just two nilpotent matrices and then you take their sum, it's not true that the sum of two nilpotent matrices is going to be a nilpotent again. But these two guys commute. So that's the second part. Left multiplication by a and right multiplication by a commute. Actually, for any two matrices, that's true. And that's just the fact that GLV is associative. So you can just take any two different guys. Let's apply this to any C. To any C. On this side, what this is? This is LA of C times B. I'm multiplying on the right by B. And here is RB of A times C. Oops. I did want to have a, sorry. Otherwise, I'm going to run into problems. That was going to be a problem. Let's do this here. So now this is just A times CA. And here is just A times CA. Let's put the B later. And now this is just by associativity, the same thing. So I have these two guys commuting. Therefore, now LA minus RA to the probably 2n. Yes, to the 2n is equal to, well, if they commute, now I just can do this 2ni LA. Well, there's going to be a sign to minus 1 to the I, perhaps. And then LA to the I, RA to the 2n minus I. But now, if I, and this sum is from I is equal to 0 to 2n. So if I is bigger than n, this guy is 0. And if I, well, bigger or equal than n. If I is less than n, then this guy is bigger than n, and this guy is 0. All right, so that shows that whenever you have an endomorphism that is nilpotent, then taking the adjoint by that endomorphism is also an nilpotent operation. The converse is certainly not true. I mean, and this is a big remark. There are matrices that are not nilpotent but their add, so matrices say A, but add A is nilpotent. A good example is the identity matrix. The identity matrix commutes with anything, so the adjoint is already 0. So in particular, it's nilpotent. But the matrix itself is not nilpotent. Any diagonal one is not nilpotent. But good examples of nilpotent matrices are upper triangular matrices. These we already know that are nilpotent. So their adjoint is also nilpotent. I said at some point that Tn, so upper triangular matrix, not even strictly upper triangular matrix. If you take the brackets of two of these guys, you get an upper triangular matrix. So somehow we're going to use this in a second. So now the statement that follows is to say that it's aiming and saying that whenever you have a Lie algebra that consists of nilpotent operators, it's going to be upper triangular matrices. So that's what we want to prove. So then we can try to start separating Lie algebras. If you have enough nilpotent operators, just take them out. Let's worry about nilpotent Lie algebras from one side. Let's worry about simple Lie algebras on the other side. All right, so theorem. I think this is angles here, or probably angles. What people call angles might be a corollary of this. Let G inside of GLV be a Lie subalgebra consisting of nilpotent operators. So they are nilpotent acting on V by multiplication. Then there exists, let's assume V is not 0 and is finite dimension. Everything here is finite. Then there exists a non-zero vector in the vector space that is killed by all the operators at the same time, such that G on V is equal to 0. So this means AV is equal to 0 for every A in G. I mean, clearly, if I had upper triangular matrices, so that's a Lie algebra consisting all of them of nilpotent operators. In this basis, there is one vector that gets killed by all upper triangular matrices, this one. So the vector 1, 0, 0, 0 everywhere gets killed by all upper triangular matrices. But the problem is that a priori I could have a Lie algebra, a sub-Lie algebra of GL, that has some matrices are upper triangular, which are certainly nilpotent, and some other matrices are lower triangular, which are certainly nilpotent. And now, how do I find one vector that gets killed by all of them? So we'll use this previous lemma. All right, so let's prove this theorem. So the proof is going to go by induction. By induction on the dimension of G. If the dimension of G is 1, this is almost obvious. I have only one operator on a vector space that is nilpotent. I want to prove that there's one vector that gets killed by that guy. Well, if an, say n plus 1, is equal to 0, but an is not 0 acting on V, an is not 0, that means that there exists something that a and b is not 0, but a times a and b is equal to 0. So this guy would do. So when the dimension is 1, we know. We have one vector that gets killed by all of G. So now let's assume that the dimension is bigger than 1. And let H inside of G be a subalgebra. A proper subalgebra. The idea is to try to find one vector that gets killed by all of H and try to extend this to the whole G. So we have some subalgebra of H of G. H acts on V, on the vector space V, by nilpotent operators. I have one vector because the dimension of this guy is less than the dimension of G. By the induction hypothesis, I can find one guy that gets killed by all of H. How do I add the extra operators coming from G that are not in H? So for this, we're going to use the previous lemma. Since H acts by nilpotent operators, the adjoint action of H, so let's see, add A is nilpotent for every A in H. That was the previous lemma. But the adjoint action of H, since G is an algebra, G is stable by this adjoint action. So H acts by nilpotent operators on G by the adjoint action. But H is a subalgebra of G. Therefore, H acts on itself. And H is a subspace that is stable by the adjoint action on G. So the adjoint representation defines a representation of H of the same subalgebra H on G mod H, on this vector space. Again, the fact that the bracket of something in H with G is still on G is the fact that G is an algebra. But the fact that H is stable is the fact that H is a subalgebra. All right, so now we have H acting by the adjoint representation, or by taking brackets on this space, and it acts by nilpotent operators. And this is by the previous lemma. Since H acted by nilpotent operators on the vector space V. All right, but now the dimension of H is less than the dimension of G, so I can find, by induction, we can find a vector, say b, inside of this vector space. Let's put a bar on it. Such that, well, the action of h on b is 0. Such that a bracket b bar, or let's write it as an adjoint, such that the adjoint action of a on b bar is equal to 0 for every a in h. This is the induction hypothesis. I have a smaller dimensional algebra acting on a vector space by nilpotent operators. I can find one vector that gets killed by the whole algebra. What does it mean to be 0 in this space? Well, let's take a preimage in G. So choose any B. Now, this is in G, a preimage of that. So this condition here, that the adjoint action of A on B bar is 0 on the quotient space, is just that the adjoint action of A acting on B, well, belongs to H. Well, which is the same for every A in H. Or the same thing, A, B belongs to H for every A in H. I didn't define you what the normalizer is, so I'm not going to mention it now. But let's put a star here so that I recall this later. All right, so here we can use a trick. We were free to use any subalgebra we wanted, and we got there. So the point is, we started with any subalgebra, H, and what we could find is an element outside of this algebra. B cannot be in H, because this vector was not 0. So the point here is that B is not in H. Otherwise, B bar would be 0 in the quotient. And we found, therefore, an element outside of the algebra such that, well, if you take the bracket of A or anything in H with this guy outside, it lands again in H. So in particular, H plus the field times B is a Lie algebra. It's a subalgebra of G. And H is an ideal inside of that subalgebra. And H is an ideal well, now we can do two things. Either I could have started here. Let H be a proper subalgebra of maximal dimension, or I could just replace H by plus FB and repeat. So feed this algebra, it's called this algebra H2, and put it back here. This is another proper subalgebra. Let's suppose it's a proper subalgebra. Just repeat, find another B2, such that this gives you a bigger algebra. At some point, you have to get to the whole algebra G. G was finite dimension. In other words, if I asked this algebra to be of maximal dimension, well, then we should have here, this is the whole G, because this is a bigger algebra. So what we ended up doing is, we found a way of expressing our Lie algebra as a sum of two algebras. Well, we have an ideal of codimension 1. And this generator out of the complement. Okay, good. So now, this was, well, hope you took note of this. All right. Yeah, I shouldn't have erased that. All right, so now, let's look at, we know, let's write this. We know there are vectors in V such that AV is equal to 0 for every A in H. There are some non-zero vectors just because of the induction hypothesis. If I have two such vectors, their sum is also such a vector. So the space of all such V's is a vector space. So let's call W is the space of V in V such that HV is equal to 0. This is a subspace of V. And it's non-empty. At least there's one. Moreover, W is G invariant. What does that mean? It means that if you give me any element, say A in G, and any V in W, then, let's say, X in H, I want to claim that A times V is again in W. But this is if and only if. Well, being in W means that for any X, X times A times V has to be 0. But this is if and only if I take their bracket, X times A times V is the same thing as, well, let's write it as X times A minus A times X plus A times X on V. This is equal to 0. And this is equal to the bracket of X with A acting on V plus A X V. The bracket of X with A, since H is an ideal, is in H. So this is 0. And here I have X of V. X is in H. So this is also 0. So W is invariant by G. Well, now we're done. We wrote down G as a sum of an ideal plus a subspace of dimension 1 generated by one operator. This whole algebra acts by 0 on this space W. And this operator preserves this space W. So I have B acting on W. And it's nilpotent. It better have a non-trivial vector that vanishes. So B is nilpotent acting on W because W is invariant by G. So there exists a non-trivial V in W such that V is equal to 0. And that certainly, so V does the trick. That proves the theorem. It's a non-trivial statement. But the point is, if we have a Lie algebra where every matrix in it, it has to be a Lie algebra inside of GLV. So it's a Lie algebra of matrices, and every matrix is nilpotent, then there's one vector that gets killed by the whole algebra. Actually, an observation, it's in those lecture notes. I remember when I took those notes. This surprised me. But it's trivial anyways. Observation. you can ask the following question. Say you have a subspace. Instead of algebra. Namely, if I give you a subspace inside of the space of matrices, consisting of all matrices that are nilpotent, is it true that you have one vector that gets killed by all of them? And the answer is no. So we really need the algebraic structure, the Lie algebra structure for this space. All right, so now the standard applications are all obvious. Let's see. I'll just write a couple of them and then we can just finish. All right. Okay, the first thing to do is the following. Say G inside of GLV consists of nilpotent operators again, dimension is finite everywhere. Then there exists a basis for V such that G consists of upper triangular matrices. Proof, just induction. So the proof is just repeat the theorem inductively. So step one, there exists by the theorem, there exists one vector V which is non-zero inside of V. Let's call it V1, which is non-zero, and the whole of G kills it. In particular, G acts on, now not on V, but on V mod V1. Well, I should say F times V1. But now you have G acting again by nilpotent operators, so pick V2. V mod F V1 such that G kills it there. But that means that if you take a preimage of V2, oops. Then we have this equation here means G V2 lives inside of the span of V1. And so forth. That way you get a flag where you would have span of V1. This is where G of V2 lives. Well, but then G of V3 would live inside of the span. Would live inside of the span of V2 plus D1 and so forth. And now choose the basis is the basis what you would get. V1 up to Vn where you finished, does the trick. Okay, good. So now, all algebras consisting of nilpotent operators are upper triangular matrices. You can write them as upper triangular matrices. Actually, I didn't need this G on GLV. I could have phrased this in terms of representations. So let's do that. So the statement is, if you have a finite dimensional representation, observation, if pi from G into some GLV is a finite dimensional representation, consisting of nilpotent operators, then there exists a basis such that pi of G is upper triangular or consists on upper triangular matrices. All right. So why we prove this kind of stuff? The idea is that from now on, we want to get rid of nilpotent algebras. I mean, upper triangular matrices, okay, fine. I mean, there's a lot to be said about the algebras of upper triangular matrices. Solvable the algebras are also quite an important subject. We'll talk about this in a second. But then we'll divide the class of at least complex Lie algebras in finite dimensional ones in two classes, this kind of algebras and the simple ones, and then we'll try to classify the simple ones. Now, let me define for any Lie algebra so that we finish defining what a nilpotent Lie algebra is. We can define a sequence, or two sequences. The central sequence is as follows. We take, I never remember if it starts with a 1 or with a 0, but let's say that G0 is equal to G. Let's say G1 is equal to G. And let's say G2 is equal GG bracket with G, and so forth. So GK plus 1 is equal to the space GK bracket with G. So this is an inductive sequence. And let's define another one. Let's say G0 is equal to G. G1 is equal to G. G2 is equal to G1. And GK plus 1 is equal to GK. Okay, so the first observation is this sequence is of inclusions. Certainly, this guy is inside of the algebra, and this guy certainly is inside of here, and so forth. this guy is inside of GK. The same here. And these are obviously proper inclusions. These are all ideals of G. These are all ideals. We can prove this in a second. We can prove this by induction. But moreover, GK, well, G0 is equal in this side, G1 is equal in this side, but now this guy here lives inside of this guy. But it may not be the same. Definition. A Lie algebra is called nilpotent and notice that I'm giving a definition of nilpotent that does not depend on having this representation in GLV. If GK is equal to 0 for some K. So if this sequence at some point stops, that Lie algebra is called nilpotent. Notice that if, say, GK plus, well, GK minus 1 is not 0, but GK is 0, right? Then what does that mean? This means that GK minus 1, G, this is by definition GK, this is 0. This means that this guy here has to be inside of a center. Because it commutes, any element here commutes with the whole algebra G. So a nilpotent Lie algebra has a non-trivial center. Because, well, GK minus 1 is non-zero. But then, I mean, we can go on. We can just take, this is an ideal, we can just grab G modulo the center. Or let's just take it modulo GK minus 1. And this guy is still going to be nilpotent. So we can play this trick and do the same thing of finding these bases that we did for upper triangular matrices. You start with a nilpotent Lie algebra, and, well, take the last one, you find that is central, mod it out, check that the quotient algebra you get is nilpotent, and try to understand that quotient. Is a lower dimensional Lie algebra, so it's easier to understand, and you can go further down. We'll probably do something about that next time, and not now. I want to finish before. Now, algebra such that this sequence stops are called solvable. So if gk is equal to 0 for some k, G is called solvable. Oops. Well, the typical example for nilpotent Lie algebras we already know. It's upper triangular matrices. And the typical example for solvable Lie algebra is non-strictly upper triangular matrices. So if I take non-strictly upper triangular matrices, is solvable, but not nilpotent, and strictly upper triangular matrices is nilpotent. Well, but then, since this ideal is inside of this guy, certainly that means it's solvable. This, by the way, allows me to correct something because it wasn't in your exercises last time. I didn't want to do the two-dimensional example, but let's work it out now because that's an example of a solvable one. Last time we said, okay, let's look at the non-abelian two-dimensional Lie algebra. I think the exercise is to find a matrix form for it. Well, then this algebra G is generated by two guys. Let's say they're called A and B, linear independent objects. So what is G1? G1 has to be generated by, well, all possible brackets of these guys. A with A is 0, B with B is 0, so this can only be A with B. So this is a generator of G1. I don't know what happens with G2 yet. But now, that's a one-dimensional space. So there better be some guy C that is not in FAB. So let's take such C. There should be a non-zero guy here. Let's put a name to this guy. Let's call this guy D. And let's look at the bracket of C with D. This bracket can only be a multiple of D, of AB. Because, well, this was an ideal. G1 is an ideal. And it's a one-dimensional ideal, so whatever bracket I take on any guy in my Lie algebra, it has to land in this one-dimensional space. So this is a multiple of D. So let's say this is, say, alpha times D. But alpha is non-zero. If alpha was 0, the algebra was commutative. All right, but then let's replace this C by 1 over alpha times C, so that this is isomorphic to the two-dimensional algebra with two generators. We can call them C and D, and the bracket of these two guys is D. And now we can compute the whole series. So if we have G, 0 is just G, G1 is F D, G2 is I take the whole G and I take the bracket with G1, and it's the same thing. And it's the same thing, and this continues. This never stops. But we get, this is G, G1 is FD, G2 is, well, now, in order to compute G2, I need to take the bracket of D with itself. So this guy is certainly 0. So this is an example of a solvable algebra that is not nilpotent. So it can't be, for the exercise, you can't be looking at upper triangular matrices. Okay, so I don't remember if I asked you in the exercise to compute, but looking at Victor notes, I see, and these are kids at MIT, so I wouldn't feel guilty if this happens, but so there are some exercises that say compute the centers of GLN, SLN, and so forth. Don't try to do it by hand. I mean, well, do it if you want, but the thing is, after what we did today, it's really easy to compute the centers of these algebras by just using a theorem instead of trying to compute what are the matrices that commute with all other matrices. If it is in the exercise, just think about what Engel's theorem says. The center is easy to find for upper triangular matrices, for example. All right. I'll see you, I guess, on Thursday. Yeah, well, if you have any questions, just send me an email, I guess. And I'm in my office every day. And you can speak Portuguese to me, I guess. All right, see you guys.